Hi class, in lesson 7.2 we will be exploring squares, cubes, and roots. Learning targets for today, we will be determining the square of a number, calculating the square root of a number, determining the cube of a number, and calculating the cube root of a number. Again, much like we saw with the knowledge rating scale, a lot of key vocabulary terms within lesson 7.2, so make sure that you make a note of those as we go through the lesson. Let's take a look at problem 1 on page 474. Linda is a landscape architect who specializes in designing backyard patio floors. She has a large collection of different square tiles that she uses to lay out her patio floor designs. When she consults with a possible client, she always takes graph or grid paper to demonstrate her designs. She's going to take that graph paper when she consults with possible clients in order to help her visualize her patio designs. Now what she needs to do is make a square patio out of 169 blue square tiles. She needs to determine how many different sized square patios she can create with 169 tiles. Linda starts with the designs shown. So take a look at all of the designs that you see here, and let's go ahead and answer number 2. What is the area of each square patio design? Go ahead and complete the table for number 2. If we take a look at the table in number 2, the dimensions for the first square are 1 by 1, which is going to give me 1 square unit. The second square patio design is 2 by 2. I'm going to have 4 square units, and the third square patio design is 3 by 3, which is going to give me 9 square units. Let's go ahead and take a look at number 3 underneath the table. It says describe the different ways that you can determine the area of each square. I'm looking for 3 different ways that you could determine the area, so go ahead and answer number 3. Come up with 3 different ways that you can determine the area of each of those squares. 3 different ways that we can determine the area of each square. The first thing that we can do is just count all of the squares that we see inside of it. A second way is to multiply the length of the square by the width of the square. And a third way to determine the area would be by squaring the length of the side. Down at the bottom of page 474, it states then that the area of a square is calculated by multiplying the length of the side by itself. The formula A equals S times S can also be written as A equals S squared. To calculate the square of a number, you multiply the number by itself 2 times. At the top of page 475, it says in question 2, you calculated the area for the first 3 square patio designs. 1 squared is equal to 1, 2 squared is equal to 4, and 3 squared is equal to 9. The 1, 4, and 9 are called perfect squares because each is the square of a whole number. For instance, 9 is a perfect square because 3 is the whole number, and 3 times 3 is 9. Another way you can write this mathematical sentence is 3 squared is equal to 9. If we take a look at number 4, it asks us to complete the grid by continuing to create squares with side lengths of 4 through 15. Now, you do not have to use a straight edge to connect the side lengths together like it has in the example for the numbers 1, 2, and 3. All I'm looking for you to do is write the math sentence using exponents to represent each perfect square. So go ahead and do that for number 4, for numbers 4 through 15. Here is what your math sentences should look like for the numbers 4 through 15. 4 squared is 16, 5 squared 25, 6 squared 36, 7 squared 49, 8 squared 64, 9 squared 81, 10 squared 100, 11 squared 121, 12 squared 144, 13 squared 169, 14 squared 196, and 15 squared 225. I want you to also remember that the exponent tells us how many times that we are multiplying the base number by itself. If we take a look at the top of page 476, it says if you know the area of a square, you can work backwards to calculate the length of the side of the square. For example, to determine the length of a side of a square that has an area of 81, you need to calculate what number multiplied by itself will equal 81. Since 9 times 9 is equal to 81, the side length of the square is 9, and 9 is called the square root of 81. A square root is one of two equal factors of a given number. Every positive number has two square roots, a positive square root and a negative square root. For instance, 5 is the square root of 25 because 5 times 5 equals 25. The symbol square root is called a radical and is used to indicate square roots. The radicand is the quantity under a radical sign. So you can see a nice diagram right here. You have the radical pointing to the symbol, and you have the quantity underneath it, the number 25, that represents the radicand. This is read as the square root of 25. That's how we are going to read it. Let's take a look at number 5. It asks us to write the square root for each perfect square. If you need to, refer back to the grid that you completed in question 4 on the previous page. Go ahead and do letters A through O. Here are the answers that you should have for letters A through O. If we just take a look at letters A, B, and C just to get, again, a good understanding. The square root of 1 is going to be 1 because 1 times 1 is going to give me 1. The square root of 4 is 2. 2 times 2 is 4. The square root of 9 is 3 because 3 times 3 gives me 9. So go ahead and take a look at the rest of the letters D through O to make sure you have the correct answers. Let's take a look at numbers 6, 7, and 8 down at the bottom of page 476. Go ahead and answer those with your group members. If we take a look at number 6, what do you think is the value of the square root of 0? Explain your reasoning. That answer is going to be 0 because I know that 0 multiplied by itself is going to give me 0 for my product. Number 7, what is the side length of the largest square Linda can create with 169 squares? Explain. The side length of the largest square Linda can create with 169 squares would be 13 because 13 would be the square root of 169 would be equal to 13. For number 8, do you think the square root of a number will always be a whole number? If not, provide an example. The square root of a number will not always be a whole number. Just one possible example is the square root of 7 because no whole number multiplied by itself is 7. Let's take a look at the top of page 477 and talk about estimating with square roots. It says that the square root of most numbers is not an integer. You can estimate the square root of a number that is not a perfect square. Begin by determining the two perfect squares closest to the radicand so that one perfect square is less than the radicand and one perfect square is greater than the radicand. Then use trial and error to determine the best estimate for the square root of the number. Let's take a look at the example. If we take a look at the example, the first thing I want you to notice is that they point out that it might be helpful to use the grid that we created back in question 4 to help you identify the perfect squares. Now what we want to do is we want to try to estimate the square root of 10 to the nearest tenth. So we want to identify the closest perfect square less than 10 and the closest perfect square that is greater than 10. So the closest perfect square that is less than 10 would be 9. The closest perfect square that is greater than 10 would be 16. We know that the square root of 9 is 3 and that the square root of 16 is 4. So this is going to tell us then that the estimate of the square root of 10 is going to be between the numbers 3 and 4. So the next thing that you have to do is choose decimals between 3 and 4 and calculate the square of each number to determine which one is the best estimate. Now what they do here is they tell you to consider the decimals 3.1 and 3.2. When you square both of those, you can see that 3.1, when you square that, you will get 9.61, When you square 3.2, you will get 10.24. So the square root of 10 is going to be approximately equal to that 9.61, which is 3.1. Let's take a look at number 9 at the top of page 478. Let's get some practice with the example that we just took a look at. We want to identify the two closest perfect squares, one greater than the radicand and one less than the radicand. And again, you can use the grid in question 4 if you need to. So go ahead and do letters A through D for number 9. The two closest perfect squares for letter A are 4 and 9. For letter B, 36 and 49. For letter C, 64 and 81. And for letter D, 81 and 90. Let's take a look at number 11 at the bottom of page 478 to finish up problem 1. We need to estimate each radical in question 9 to the nearest tenth and explain our reasoning. So go ahead and do letter A through D for number 11. Let's take a look at each of these one by one so that we get an understanding of how to estimate each of these radicals to the nearest tenth. If we take a look first at letter A, we're trying to figure out the square root of 8, trying to estimate the square root of 8, and we set up a number 9 that the two perfect squares that we were going to use were 4 and 9, so we know that the square root of 4 is going to be 2, the square root of 9 is going to be 3. So our decimal then is going to be between the whole numbers 2 and 3. Now remember, you're supposed to use trial and error, and when you do that, 2.8 squared is going to give you 7.84. That's going to be the closest that you can get to 8. So the square root of 8 then is going to be approximately equal to 2.8. If you take a look at letter B, we're trying to find the estimate for the square root of 45. We set up in letter A that we were going to be using the perfect squares of 36 and 49. The square root of 36 is 6. The square root of 49 is 7. So we know that the decimal is going to be in between the numbers 6 and 7. The square root of 45 is going to be approximately equal to 6.7, because when you square that number, you are going to get 44.89 for your decimal. That's going to get you as close as you can to 45. If we take a look at letter C, the square root of 70, we said in number 9 that we were going to use the perfect squares 64 and 81. The square root of 64 is 8. The square root of 81 is 9. So we know that our answer is going to be between the numbers 8 and 9. The square root of 70, again using trial and error, is going to be 8.4, approximately 8.4, because when we square that decimal, we get 70.56 for our answer. That's going to get us as close as we can to 70. And finally, for letter D, the square root of 91, we were using the perfect squares 81 and 90. The square root of 81 is 9. The square root of 100 is 10. The square root of 91 is going to be approximately 9.5, because when we square that decimal, we're going to get 90.25. That's going to get us as close as we possibly can get to 91. If we take a look at problem 2 on page 479, now we will take a look at cubes. Problem 2 is set up very similar to the format of problem 1 as far as how you are going to be working through the problem. Let's take a look first at number 1. It says, use unit cubes to build a cube with side lengths of 1 unit, 2 units, and 3 units. So take a look at number 2 and go ahead and complete the table. If we take a look at the table, the dimensions of the cube for 1 unit are going to be 1 by 1 by 1 to give us 1, the number of unit cubes, 1 cubic unit. For 2 units, we will have 2 by 2 by 2 for 8 cubic units. And for 3 units, we will have 3 by 3 by 3 for 27 cubic units. 4 by 4 by 4 is filled in for you. that will give us 64 cubic units. If we take a look underneath the table, it says the volume of a cube is calculated by multiplying the length of the cube by the width of the cube by the height of the cube. The formula V, which stands for volume, is equal to S times S times S. It can also be written as V equals S cubed. In question 1, you calculated the volume of 3 cubes whose side lengths were the first 3 counting numbers. 1 cubed equals 1, 2 cubed equals 8, and 3 cubed equals 27. The numbers 1, 8, and 27 are called perfect cubes. A perfect cube is the cube of a whole number. For example, 64 is a perfect cube since 4 is a whole number, and 4 times 4 times 4 is equal to 64. In order to calculate the cube of a number, you multiply the number by itself 3 times. Let's take a look at number 3 on the top of page 480. It is asking us to calculate the cubes of the first 10 whole numbers. So go ahead and do letters A through J. Here are your answers for letters A through J. A through D was already done for us in the table. 1 cubed is 1, 2 cubed is 8, 3 cubed 27, 4 cubed is 64. Remember, we're multiplying that whole number by itself 3 times. That's what that exponent tells us. For letter E, 5 cubed 125, 6 cubed 216, 7 cubed 343, 8 cubed 512, 9 cubed 729, and 10 cubed 1000. Continuing on page 480, much like we did with square roots in problem 1, if you know the volume of a cube, you can work backwards to calculate the side lengths of the cube. For example, to determine the side lengths of a cube that has a volume of 125, you need to calculate what number multiplied by itself 3 times will equal 125. Since 5 times 5 times 5 is equal to 125, a side length of the cube is 5 and is called the cube root of 125. A cube root is one of 3 equal factors of a number. As with the square root, the cube root also uses a radical symbol, but has a 3 as an index. The index is the number placed above and to the left of the radical to indicate what root is being calculated. Let's take a look at number 4. We are asked to write the cube root for each perfect cube, so go ahead and answer letters A through J. Here are your answers for A through J. The cube root of 1 is 1. The cube root of 8 is 2. Cube root of 27 is 3. Cube root of 64, 4. Cube root of 125, 5. Cube root of 216 is 6. Cube root of 343 is 7. Cube root of 512 is 8. Cube root of 729 is 9. And the cube root of 1000 is 10. Let's go ahead and finish up page 480 by answering number 5 and number 6. What is the side length of the largest cube you can create with 729 cubes? And for number 6, will the cube root of a number always be a whole number? If not, provide an example of a cube root that is not an integer. So go ahead and do number 5 and 6. For number 5, the side length of the largest cube you can create with 729 cubes would be 9, because the cube root of 729 is equal to 9. For number 6, the cube root of a number will not always be a whole number. This is very similar to what we saw in problem 1 when we were talking about square roots. One possible example that we could look at is the cube root of 7, because no whole number multiplied by itself 3 times is going to be equal to 7. Let's take a look at the top of page 481. Most numbers do not have whole numbers for their cube root. Let's estimate the cube root of a number using the same method used to estimate the square root of a number. Let's take a look at our example. To estimate the cube root of 33 to the nearest tenth First, identify two perfect cubes closest to the radicand. One of the perfect cubes must be less than the radicand, and the other must be greater than the radicand. Then use trial and error to determine the best estimate for the cube root. The closest perfect cube that would be less than 33 is 27, and the closest perfect cube greater than 33 is going to be 64. We know that the cube root of 27 is 3, the cube root of 64 is 4, so this means that the estimate of the cube root of 33 is going to be between the whole numbers 3 and 4. So now again, we are choosing decimals that are between the numbers 3 and 4 and calculating the cube of each decimal to determine which one is the best estimate. In this case, we can see in our examples here that 3.2 cubed gives me 32.768, which is as close as I can get to 33. So I know then that the cube root of 33 is approximately equal to 3.2. Let's finish up lesson 7.2 by looking at number 7 on page 482. We want to identify the two closest perfect cubes, one greater than the radicand and one less than the radicand. Then we want to estimate each cube root to the nearest tenth. So go ahead and do letters A, B, and C with your group members. Let's take a look at letter A. 100 is going to be between the two perfect cubes of 64 and 125. The cube root of 64 is 4, the cube root of 125 is 5, so we know that our answer is going to be somewhere in between those two whole numbers. The cube root of 100 then is going to be approximately equal to 4.6. When I use my trial and error, 4.6 cubed is going to give me 97.336. That's as close as I can get to 100. So 4.6 is my approximate answer. If I take a look at letter B, 175 is between the two perfect cubes 125 and 216. The cube root of 125 is 5. The cube root of 216 is 6. So I know that my answer is going to be in between those two whole numbers. The cube root of 175 is going to be approximately 5.6. Again, when I use my trial and error, 5.6 cubed gives me 175.616. So 5.6 is as close as I can get to 175. And finally, for letter C, 256 is between the two perfect cubes of 216 and 343. The cube root of 216 is 6. The cube root of 343 is 7. So I know my answer is going to be somewhere between 6 and 7. The cube root then of 256 would be approximately 6.3. When I cube 6.3, I get 250.047. That's as close as I can get to 256. So my answer is 6.3. That's going to be it for lesson 7.2 on exploring squares, cubes, and roots. Please let me know if you have any questions. Thanks.